Thin-walled cylinder analysis is my project. This presentation will act as a record of what I have done so far and my progress in this report. Thin-walled elements, especially cylinders, are widely used in engineering design as they allow for the manufacture of lightweight but strong structures in many applications. These applications include aircraft fuselages and cylindrical structural supports. For load-bearing thin-walled structures, the impact and effects of buckling is of great significance, as it is often the primary limiting factor for safe design load. And if buckling failure were to occur, it could pose a catastrophic risk for the structures that use this type of element. The image shown in this slide is the geometry of the thin-walled cylinder, which includes its length, its outer diameter, and inner diameter. For the aluminium alloy simulations, the following tests will be done. First, it will be given a length of 750 millimeters, a diameter of 450 millimeters, and a 4 millimeter wall thickness. This gives a thickness on diameter ratio of 0.0089. The length will then be changed to 1000 millimeters and then to 500 millimeters without changing the other dimensions. Then, the thickness is changed to 5.5 millimeters with the same diameter as above to give a thickness on diameter ratio of 0.0122. Then, the diameter is changed to 250 millimeters with the same thickness as above to give a thickness on diameter ratio of 0.016. The next comparison test that will be done on aluminium alloy is the symmetrical versus anti-symmetrical loading cases. In the symmetrical case, a force of 1000 newtons is applied and distributed evenly across the cross-sectional area of the cylinder, whereas in the anti-symmetrical loading case, 1000 newtons will be applied on 1/2 of the cross-sectional area of the cylinder. The simulations run on the carbon epoxy composites will include the comparison between symmetry and anti-symmetry using the two following apply sequences: -45, /45, /0, /90, and the other 90, /0, /0, /90. The following are the boundary conditions for all simulations. The support at the bottom of the cylinder was modeled as a fixed support, acting on the bottom of the cross-sectional area. The top of the cylinder is restricted, but is allowed 1 degree of freedom in the vertical Z direction. For all simulations, the following meshing and element type were used. Tetrahedral elements were used, as even though they take up a lot of power, they give accurate results, and shell body type was used to reduce the computing time. Additionally, nonlinear analysis was used as it would lead to a more accurate solution. There are two solution types. For the aluminium alloy simulations, static structural and eigenvalue buckling will be used. For composites, in addition to those two, there will be ACP pre and post used as well. As a means of validation and to derive the element sizing that will be used for all the simulations, a convergence study was done. By using a variety of element mesh sizes and plotting its effect on equivalent von Mises stress, it can be seen that the stress converges at 2 mm element size. Therefore, this size was used for all simulations. The following slides will visualize and tabulate the results of the ANSYS simulations. The following image shows the ANSYS result for equivalent stress for the anti-symmetrical loading case. The maximum stress is 0.28 megapascals. As expected, it occurs on the side of the cylinder where the loading is applied. Using the eigenvalue buckling module, we can find the different buckling modes for the anti-symmetrical loading case. As you can see, the total deformation for buckling mode 1, 2, 3, and 4 are shown below. For the symmetrical loading case, as expected, the loading is much more distributed evenly throughout the structure. The maximum equivalent stress is 0.217 megapascals. In a similar way to the previous test, buckling modes are shown below for the symmetrical loading case, with total deformation and loading multiplier being shown. The results are tabulated below. Using parameters and parameter sets in both the symmetrical loading and anti-symmetrical loading ANSYS files, we can find the total deformation, critical buckling load, and equivalent stress for each change in geometry. This comparison table shows the maximum total deformation according to loading and geometry. Finally, by using the load multiplier from the ANSYS results and multiplying that by the load, which is 1,000 newtons, we can get the critical buckling load for each loading case and geometry. Extensive research, no equations were found for composites with a critical buckling load to appropriately and accurately validate the model. According to our boundary conditions, K in this instance is 1 as both ends of the cylinder are fixed. To convert the problem into a mathematical model, the following equations are used. The critical buckling load for long columns can be modeled as such. Pi times the Young's modulus of the material times the second moment of inertia of the structure divided by the effective length factor times the length of the cylinder, all squared. Finite element analysis has limitations, and it cannot properly and accurately model the real world. The accuracy of the finite element solution depends on the mesh size, which has its limits due to the student license I am currently using. It splits up a complex problem into smaller problems that then glue them back together into an approximate solution. Additionally, it does not solve for material direction and other manufacturing specific problems. The missing components of this project are the carbon epoxy simulation results, validation, and a discussion of errors, as well as the use of more case studies to compare with the results. This concludes my presentation. Thank you for listening.